Chapter 1. The Search for Ancient Earth. A Scientific Investigation. From orbit, the night side of Earth looks like a giant neural network pulsing with electric light. But if I hit fast forward on this cosmic timeline, something unsettling happens. The illusion of permanence crumbles. The lights go out. The pumps that keep London's and New York subway systems dry fall silent, and the tunnels flood within days. Without constant maintenance, entropy immediately claims its territory, beginning the total dismantling of our civilization. Let's pause here for a moment. The materials we think of as permanent Fae, the ones our cities are built from Fae, are geologically laughable in their fragility. Reinforced concrete, the backbone of our urban world, has a lifespan measured in hundreds, not millions of years. The carbonation process in concrete lowers its alkalinity, causing the steel reinforcement to corrode and literally explode the stone from within. Glass and plastic, under ultraviolet radiation and temperature cycles, break down into microscopic dust that mingles with soil. Within 10,000 years, Fae a blink of an eye in planetary terms, Fae erosion would erase the last visible traces of our architecture. The glaciers of the next ice age would sweep across the northern hemisphere like giant sandpaper, grinding the ruins of megacities into gravel. Then, tectonic forces would take over. The slow but relentless drift of continents would send entire crustal layers into subduction zones to be remelted in the mantle. To understand the scale of this destruction, we need to grasp the true age of our stage. Earth is 4.5 billion years old. This number is so vast that the human brain, evolved for planning hunting seasons, simply refuses to process it. We're trying to measure an ocean of time with the teaspoon of our historical memory. So, let me propose a more visual scale. Let's compress the planet's entire history into a single day. In this model, Earth forms at exactly midnight. The first simple life appears around 4 a.m. Dinosaurs emerge on land at 10:40 p.m. and disappear just 20 minutes before the day ends. Where are we in this timeline? Anatomically modern humans appear at 11:59 and 56 seconds. We get just 4 seconds total. Our entire industrial civilization, Fae factories, satellites, nuclear weapons, Fae exists for only the last 0.002 of a second. We're a flash that the geological chronometer doesn't even have time to register. In these 200 years of active industry, we've convinced ourselves that we've conquered nature. But geology teaches us humility. The half-life of most of our building materials is nothing compared to the epochs that lie beneath our feet. The planet isn't just a rock Fae, it is an active acid bath constantly digesting its surface, erasing any signatures we might leave behind. Picture a geologist of the future drilling core samples 50 million years from now. What would they find where modern Shanghai or Moscow once stood? There would be no statues, no hard drives with data, no automobiles. Everything that remains from our proud technocratic era would be compressed into a thin, barely noticeable layer in the sedimentary rock. Just a few centimeters thick, this strip would differ from adjacent layers only in its anomalous chemical composition. A spike in nitrogen concentration from fertilizers, a layer of rare earth metals from our electronics, and of course, radioactive isotopes. We would become a geochemical signal Fae, a strange fluctuation on a mass spectrometer graph that would still need proper interpretation. This fact leads us to a disturbing paradox. We search the universe for intelligent life, scanning radio signals from distant stars, building giant telescopes. But we know our own history remarkably poorly. If traces of advanced civilizations are erased so quickly and so completely, then our confidence that we're the first and only masters of Earth might just be an illusion based on incomplete data. Official science maintains that only biological species ruled here before us face species that knew no technology. But this assertion is based on the absence of discovered artifacts. And as we've just established, the absence of artifacts after millions of years is the norm, not the exception. The geological record is a book with 99% of its pages torn out. I am not advocating belief in myths about Atlantis or ancient aliens. I am proposing we conduct a rigorous scientific experiment. If millions of years ago, an industrial civilization comparable to ours in power had existed on Earth, could we find any evidence of its existence today? Or has time already committed the perfect crime, destroying all evidence? This isn't just a question about the past, Faye. It is a question about our future. By understanding how the planet erases history, we can understand whether anything will remain after us. We're beginning this investigation with a clean slate, and the first question I am asking myself, and you, if we disappear today, will they find us in 50, or will Earth forget us, just as it may have forgotten someone before us? Chapter 2. The Vanishing Act. To find an honest answer to this question, we need to come down from the heavens to Earth. Literally, a geochemist stands at the edge of a coal quarry, watching as an excavator's bucket thunderously bites into a black layer of rock. To a layperson, this is just fuel fade dirty coal. But for a specialist who reads planetary history through isotopes, this quarry is nothing less than a compressed archive, and the news it tells us is discouraging. The visual traces of our civilization will disappear first, and this will happen almost instantaneously by geological standards. The specialist picks up a piece of heavy black rock. In this small stone, millions of years of biological history are compressed, transformed by pressure and temperature into a faceless carbon mass here. In this cold stone lies the key to the main paradox of searching for ancient civilizations. We look for familiar forms, temple ruins, machine skeletons, concrete foundations. But entropy is a merciless eraser that works around the clock, grinding any complex structures down to elementary dust. It seems to us that our cities are built for centuries. Skyscrapers of glass and concrete, bridges of alloyed steel. All of this looks monumentally permanent. However, material science dictates different timescales. Under the influence of moisture, oxygen, and temperature fluctuations, concrete begins to degrade and crumble into sand. In less than 10,000 years, steel structures, deprived of anti-corrosion protection, turn to rusty powder even faster. For a planet whose age is measured in 4.5 billion years, 10,000 years isn't even a second. It is a moment impossible to notice with the naked eye. The geochemist sees in this piece of coal a reminder of how Earth handles any organic matter and structure. If we disappear today, then in just a couple of tens of thousands of years, nothing would remain of New York or Moscow that would resemble a city. Jungles and forests would digest the remnants of buildings, tree roots would shatter foundations, and water would complete the dissolution process. We often overestimate the durability of our world, forgetting that we're fighting erosive forces that were sharpening mountains long before the first human appeared. But what about dinosaur bones, you might ask? We find skeletons of creatures that lived 60 or even 100 million years ago. So physical traces do survive, right? Here is where the brutal statistics of paleontology come into play. Fossilization is the rarest lottery, with winning tickets going to only a few. By current calculations, less than 1% of all living creatures that ever existed on the planet undergo fossilization. All the others simply disappear without a trace in the biological cycle. For a bone to turn to stone, an animal must die under specific, almost unique conditions. For example, instantly drown in an oxygen-free swamp or be buried under a layer of volcanic ash. If a hypothetical civilization lived in comfortable conditions, cremated their dead, or stored them in ordinary soil, the chances of finding their remains after 50 million years equal absolute zero. We display in museums only a tiny sample of the lucky ones who miraculously avoided complete decay. The problem is compounded not only by erosion from above, but also by movement from below. Earth's crust isn't a frozen foundation, but a dynamic conveyor belt. Tectonic plates constantly move, colliding and diving under each other in subduction zones, remelting in the mantle. This process completely renews the ocean floor every 180 million years. If an ancient civilization built their cities on ocean shelves or islands, all these territories have long since been destroyed, melted, and turned into new magma. The planet's hard drive has been formatted at a physical level, even on continents that seem more stable. Finding truly ancient surfaces is an extraordinary task. Erosion, glaciers, and volcanism constantly rewrite the landscape. The oldest surface on Earth that hasn't undergone serious changes is the Negev Desert. But it is only 1.8 million years old. Everything older has already been either washed into the ocean or buried under kilometers of new sedimentary rocks. Searching for artifacts on such a surface is like trying to read text that has been written over with new ink thousands of times in a row. Standing in the middle of the quarry, the geochemist realizes the scale of this illusion. Our entire anthropogenic layer, Fey cities, roads, landfills, will compress in geological time into the thinnest layer, just a few centimeters thick. A strange, unnatural stratum of rock squeezed between eras. No statues, no books, no microchips. The pressure of overlying rocks will flatten our automobiles to foil thickness, and high temperatures in the depths will change their molecular structure. This is why traditional archaeology is powerless here. Digging the earth in search of ancient iPhones or golden jewelry from the Paleocene is a pointless endeavor. We're looking in the wrong place, and for the wrong things. Physical objects are too fragile, a form of information storage for such colossal time spans. Time is acid, dissolving any form and leaving only content in the form of chemical elements. If we want to find predecessors, we need to stop looking at the shape of stones and start looking at their composition. We must abandon visual perception of history. Eyes deceive us. They look for familiar outlines, right angles, processed surfaces. But after 50 million years, there will be no right angles left. Only chemistry will remain anomalous concentrations of elements that shouldn't exist in nature, and isotopic shifts that cannot be explained by volcanoes or climate cycles. The trace of civilization isn't a pyramid rising above the sands. It is a mass spectrometer graph where the curve suddenly shoots upward, breaking the natural order of things. This conclusion changes the entire strategy of our investigation. We stop being Indiana Joneses with brushes and shovels. We become forensic experts on a planetary scale. The evidence we're looking for is invisible to the eye. It is hidden inside atomic lattices of minerals, in bubbles of ancient air frozen in ice or amber. The geological record destroyed the text, but it couldn't destroy the ink with which it was written. In the next chapter, we'll head to the sterile coolness of a laboratory, to arm ourselves with the most powerful tool humanity has for peering into the past. We'll learn to see the invisible. If the physical bodies of ancient civilizations have disappeared, then their chemical shadow should have remained. And this shadow has a very specific scientific name, introduced by astrophysicists in 2018. We're proceeding to test the Silurian hypothesis. Chapter 3. Reading the chemical fingerprint. Leaving the noisy quarries and windswept wastelands, where erosion mercilessly erases physical forms, we move into a space of absolute sterility. Here, behind the hermetic doors of an isotopic geochemistry laboratory, the age of archaeologists with shovels ends, and the era of physicists with detectors begins. In this silence, broken only by the monotonous hum of vacuum pumps, the search for ancient civilizations transitions from the macroscopic level to the atomic. If nature destroyed the body of a hypothetical predecessor, then its chemical blood should still be circulating in the planet's veins. At the center of the geochemist's attention is a mass spectrometer, FE, a complex device capable of weighing individual atoms. For this instrument, a piece of coal or a capsule with ancient air isn't just geological samples, but encrypted messages. The principle of this device's operation resembles coin sorting. Powerful magnets separate the flow of ionized particles, forcing lighter atoms to deflect more strongly than heavy ones. It is in this difference of trajectories, measured in nanometers, that the answer to our film's main question is hidden for an observer watching the graphs running across monitors. One fundamental truth is obvious. Industrial civilization is first and foremost a voracious energy monster. Any advanced society seeking to go beyond muscle power inevitably comes to burning hydrocarbons, and this process leaves a trace that cannot be washed away by water or erased by wind. This isn't just smoke, it is a global change in the atmosphere, is chemical balance that future geologists could read even through hundreds of millions of years. It was precisely this logic that NASA's Goddard Institute director Gavin Schmidt and astrophysicist Adam Frank used as the foundation for their work. In 2018, they published a revolutionary paper titled The Silurian Hypothesis. This wasn't a science fiction script, but a rigorous scientific challenge. Are there markers in nature capable of unambiguously distinguishing technological activity from natural geological processes? And the answer was found in Mendeleev's table in the sixth cell. Carbon. Carbon exists in nature as two stable isotopes, light carbon -12 and heavier carbon -13. To a layperson, they're indistinguishable, but for the biosphere, the difference is colossal. Living nature is lazy. During photosynthesis, it is energetically advantageous for plants to capture light atoms of the 12th isotope, ignoring the heavy 13th ones. Therefore, any plant, any animal, and consequently any fossil fuel Fe oil, coal gas Fe, is enriched with precisely this light carbon. The geochemist sees in this mechanism an ideal chronometer. While fossil fuel lies in the depths, this light carbon is safely locked away. But as soon as an industrial civilization appears, and begins massively burning the depths for energy, an explosive release occurs. Gigantic masses of carbon -12 are expelled back into the atmosphere. This instantly changes the planetary ratio of isotopes. In the geological record, this looks like a sharp dip on the graph, which scientists call a negative isotopic anomaly. Volcanoes, which are the main natural suppliers of carbon dioxide, cannot create such an effect. Carbon emerging from Earth's mantle has a completely different isotopic signature. it is much heavier. Therefore, when a mass spectrometer records a sharp drop in the proportion of the 13th isotope against the background of growing overall carbon dioxide concentration, the scientist understands this wasn't geology at work here, This was biology burning on an industrial scale. This chemical fingerprint is called the Seuss effect. And we, right now in the 21st century, are inscribing it into Earth's geological history in giant letters. If in 50 million years, intelligent beings take a rock sample formed in our era, they'll see this peak. They won't need our cities or bones. The ratio of isotopes will tell them everything. Here was a civilization that found ancient carbon reserves and burned them in a couple of centuries. But the Silurian hypothesis poses the question point. Blank, was our peak the only one? Looking at the graph of atmospheric isotopic composition over the last 500 million years, the geochemist searches for similar spikes in the distant past. They don't need fantasies about reptiloids, they need dry numbers. If someone ruled Earth before us and built a developed industry, they were obligated to leave exactly the same chemical signature. The laws of thermodynamics and chemistry are the same for everyone, whether humans, lizards, or intelligent mollusks. The problem with the search lies in data resolution. In geological layers, millions of years are often compressed into centimeters of rock. A short, bright civilization that existed, like ours, for just a couple of centuries, could simply be lost between samples taken at 1,000-year intervals. However, there are events so large-scale that their trace is impossible to miss. Events when the planet's climate broke so sharply as if someone had floored the gas pedal. The mass spectrometer analyzer displays data from cores extracted from the ocean floor. The curve showing planetary temperature runs smoothly for millions of years. Then suddenly, at the 56 million year mark, shoots vertically upward. This isn't just warming. This is thermal shock that nearly killed all ocean life. Geologists call this event the Paleocene, Eocene Thermal Maximum. At that moment, such a quantity of carbon was thrown into the atmosphere that it is comparable to burning all known reserves of oil, gas, and coal on modern Earth. Temperature jumped 5 to 8 degrees Celsius. Oceans acidified, ecosystems collapsed, and most importantly, isotopic analysis shows that same light carbon, -12 signal characteristic of burning organic matter, not volcanoes. The geochemist stares at this peak with alarm. The coincidence is frightening. We have a motive, we have a murder weapon, and we have a corpse, a planetary scale climate catastrophe. Official science explains this through natural factors, massive melting of methane hydrates, or colossal peat bog fires. But the mass spectrometer data is dispassionate. The chemistry of that event suspiciously resembles the chemistry of our Anthropocene. We stand before a paradox. We searched for traces of civilization and found a global catastrophe. Perhaps they're the same thing. The Silurian hypothesis forces us to reconsider the history of this cataclysm. Could this emission have been not an accidental planetary burp, but the final chord of someone's industrial era? An era that ended with atmospheric overheating and the complete extinction of its creators? In the next chapter, we'll leave the sterile laboratory and travel 56 million years back to the very epicenter of this hell. We'll try to reconstruct the chronology of the Paleocene, Eocene maximum events, to understand whether natural volcanoes could have acted with such surgical precision, or whether we're looking at the aftermath of millions of ancient factories whose ruins long ago became dust. Chapter 4. Reconstructing an ancient apocalypse. We're leaving the sterile quiet of the laboratory, but the answers lie far from cozy university offices. A paleoclimatologist, currently on a drilling platform in the North Atlantic, sees confirmation of these graphs, not on a screen, but in a dirty, heavy cylinder of rock. Storm winds rock the tower, and icy spray floods the deck. But all the scientist's attention is riveted to a fresh core raised from kilometer depths. In this column of compressed mud, there is a strange dark stripe that looks like a scar on the body of geological history. This stripe is the physical embodiment of that same peak on the graph we saw earlier. For a specialist, this layer speaks more eloquently than any words. This is a carbonate dissolution zone. 56 million years ago, the ocean became so acidic that the shells of marine organisms simply dissolved, leaving behind only this dark, lifeless clay. We're looking at the graveyard of the Paleocene, Eocene Thermal Maximum era. If we want to understand the nature of this killer, we need to reconstruct the crime scene. Discard the familiar image of Earth with its white polar caps. At the moment when this dark layer formed, the planet was unrecognizable. Temperature had jumped 5 to 8 degrees almost instantaneously by geological standards. Ice didn't exist. Ocean levels were tens of meters higher than today. On Antarctica's shores, where today temperatures plunged to -60, lush subtropical forests rustled, and crocodiles swam in the warm waters near the pole. This was a greenhouse world faced sultry and humid. But what is frightening isn't the heat itself. Earth had known hotter periods. What is frightening is the speed with which this heat arrived. Analysis of sedimentary rocks shows that the carbon emission occurred not over millions of years, as happens during slow continental drift, but over mere thousands, possibly even hundreds of years. This was thermal shock from which the biosphere couldn't recover for 150,000 years. The main evidence in this investigation is the volume of carbon. To heat the planet to such values, a gigantic quantity of greenhouse gases had to enter the atmosphere. We're talking about thousands of gigatons of carbon. For comparison, this is equivalent to taking all currently known reserves of oil, coal, and natural gas and burning them simultaneously. Such a coincidence of volumes makes one wonder whether we're dealing with a natural phenomenon or something else. Traditional geology offers us the main suspect, methane hydrates. These are frozen compounds of water and gas that accumulate on ocean floors. Theory states that volcanic activity or current changes could have destabilized these deposits. Methane, bursting to the surface, oxidized into carbon dioxide and created a greenhouse dome. This is an elegant theory, but it has flaws that don't give our paleoclimatologist on the drilling platform any peace. The problem lies in selective extinction. During the Paleocene, Eocene Maximum, foraminifera, microscopic organisms living on ocean floors suffered the most. Their populations decreased by 30 to 50%. This suggests that ocean acidification proceeded not from top to bottom, as with atmospheric saturation, but had more complex mechanisms. The ocean became toxic too quickly. Water chemistry changed so sharply, as if industrial waste had been dumped into it on a planetary scale. This is precisely where the logic of the Silurian hypothesis comes into play. We see an event that perfectly mimics the consequences of industrial activity. Sharp emission of light carbon-12 isotope, global warming, ocean acidification, species extinction. If we humans disappeared today, then in 50 million years, geologists would find exactly the same picture in the layers of our era, a dark clay layer devoid of carbonates, and a sharp temperature jump. Another strange fact from that period is evolutionary dwarfism. Under conditions of heat and altered atmospheric chemistry, many mammals of that time sharply decreased in size. Ancestors of modern horses, for example, became the size of house cats. The biosphere was trying to adapt to stress by reducing resource consumption. This resembles how ecosystems react to pollution and habitat degradation in our time. But if this was a civilization, where are their cities? Where are the remains of machines? Remember what we discussed earlier. Over 56 million years, erosion and tectonics erase everything. The dark layer in the core that the scientist holds might be all that remains of their skyscrapers, their plastic, and their bones. All of this was processed by bacteria, dissolved by acid, and compressed by pressure into a thin chemical anomaly. Skeptics will rightfully point to the volcanic province in the North Atlantic that was active at that time. Volcanoes could indeed have triggered this process, but modeling shows that to achieve such an isotopic shift, volcanoes would have had to work in a regime that doesn't quite fit normal eruption physics. They would have needed to burn organic sediments rich in carbon, and do so with incredible efficiency. We face a choice between an incredible coincidence of natural factors and the frightening possibility of predecessors' existence. The Paleocene-Eocene maximum lasted about 150 to 200,000 years before the planet could absorb excess carbon and cool down. This was a prolonged fever period. If this was a civilization, they didn't just die they triggered a mechanism that changed Earth's face for thousands of years after their disappearance. The paleoclimatologist stores the core in a protective container. For them, this piece of rock isn't just a geological sample, but a warning. They see a mirror in it. The event from 56 million years ago shows us our own possible finale. The difference is only that we know the cause of our warming, while the cause of that ancient one is hidden behind a veil of time. However, we have a way to test this hypothesis for strength. It is one thing to find similar crimes in the past, and quite another to compare fingerprints in detail. We need to overlay the graph of the Paleocene, a scene maximum, onto the graph of our Anthropocene. If they match not only in general features, but also in the dynamics of temperature acceleration, this would become the weightiest argument in favor of our not being the first to play with climate. We've collected the evidence: global warming, isotopic anomaly, ocean acidification, and strange biological mutations. But to definitively reclassify this case from natural disaster to man-made catastrophe, we need an expert of a different profile. We need to understand whether the physics of natural heating differs from industrial heating. In the next chapter, we'll transfer this data to an astrobiology theorist. We'll have a supercomputer compare the two hottest periods in Earth's history. And what we see in the overlay of these graphs will make us look anew at the smoking stacks of our own factories. Perhaps history doesn't just repeat itself, it follows the same script of self-destruction. Chapter 5. When Physics Meets History. A thermal imager pointed at a modern metropolis sees not people or architecture. It registers only colossal patches of infrared radiation. To an outside observer, our cities are primarily thermodynamic anomalies, phase zones where entropy grows at a frightening rate. It is this thermal map that we must overlay on events from the deep past to understand the nature of that ancient catastrophe. In the sterile coolness of a server room, an astrobiology theorist launches a simulation. The hum of supercomputer coolers drowns out thoughts while algorithms process massive data arrays. Their task is to conduct a confrontation between two suspects: our industrial civilization and the mysterious event that occurred 56 million years ago. If the graphs match, we'll have the strongest evidence that Earth's history is cyclical. On the screens, two curves unfold. The first is the graph of the Paleocene, Eocene Thermal Maximum. The second is the curve of our Anthropocene. The similarity astounds even skeptics. In both cases, we see a sharp knife-like temperature rise and identical changes in carbon isotopic composition. Ancient Earth's atmosphere was saturated with precisely that light 12th isotope that today our coal power plants and internal combustion engines spew forth. However, with detailed scaling of the graphs, the astrobiologist notices a critical discrepancy that could destroy the entire theory's speed. According to calculations, modern humanity releases carbon into the atmosphere approximately 10 times faster than it happened during the ancient cataclysm. We burn reserves that accumulated over millions of years in mere centuries. The ancient warming developed more smoothly. This observation creates a dangerous paradox. If a civilization operated 56 million years ago, it was either much slower than ours or used fundamentally different energy sources that didn't give such an instantaneous peak. Oxygen isotopes in sedimentary rocks confirm the planet's heating then started not with a vertical takeoff, but in a crescendo taking thousands of years. Skeptics triumph. The smooth graph points to natural causes. As the main accused, geology offers the North Atlantic igneous province. Monstrous volcanic eruptions could have pierced organic, rich sedimentary rock layers and set them on fire. This would explain both the light carbon emission and the process's temporal extension. It would seem the case is closed. These were volcanoes, not factories. But the astrobiologist isn't rushing to shut down the simulation. The equation has variables that don't fit the volcanic model. In cores dated to the thermal maximum period, unexplained spikes in metal concentrations have been discovered: zinc, vanadium, and molybdenum. In nature, such elements are scattered, but in a technogenic environment, they concentrate in ore enrichment and alloy production processes. The presence of these metallic anomalies forces us to return to the hypothesis of artificial origin. Volcanoes do release metals, but not in such specific proportions. This looks like a geochemical echo of global industry. But how then do we explain the smooth warming graph, so different from our industrial explosion? The answer may lie in the imperfection of our geological memory. The astrobiologist inputs a correction for so-called bioturbation, PHE, the mixing of soil layers by worms and mollusks. This process works like a blur filter in a graphics editor. If our civilization disappeared today, our sharp century-long emission peak would be smeared across a rock layer several centimeters thick in 50 million years. Mathematical modeling shows a frightening result. A short but intense event, such as all of human history, could look much longer and softer in the geological record than it actually was. Sedimentary rocks simply don't possess sufficient temporal resolution to fix a moment lasting 300 years. We look at the ancient graph and see a smooth hill, but perhaps behind it hides the sharp needle of catastrophe. There is another frightening possibility. What if the Paleocene Eocene Maximum wasn't the flowering of civilization, but its death throes? Perhaps we're seeing traces of unplanned development, PHE of final war or planetary scale accident, that led to the destabilization of methane deposits on ocean floors. An explosive hydrate release could have been that very trigger we mistake for a natural process. The graph comparison leads us to a dead end. The Anthropocene and ancient maximum data are too similar to ignore the connection, but different enough to cause doubt. The carbon footprint is circumstantial evidence. Nature can imitate light carbon emissions, albeit with difficulty. To bring charges against the past, we need evidence that nature cannot create under any circumstances. The astrobiologist understands. We need to look not for what resembles us, but for what is fundamentally alien to the biosphere. Carbon dioxide, methane, metals, Fe, all these are natural components of the planet. But there are substances whose synthesis requires intelligence and complex technological chains. Substances whose complex molecular bonds cannot arise in the chaos of volcanic eruption. If we want to find the truth, we'll have to shift our gaze from temperature graphs to the bottom of the world ocean. We must search for materials that don't dissolve in water and aren't digested by bacteria. We need techno-fossils, fossil remains of technologies. And humanity already has a candidate for the role of eternal marker that we're leaving as an inheritance to future geologists. In the next chapter, we'll descend to the microscopic level, where among grains of sand and silt, polymers hide. We'll see how the material we've created becomes part of the geological cycle, and learn whether plastic can survive 50 million years of pressure and temperature to tell future beings about us. Chapter 6. The Plastic Archive. The carbon footprint, for all its significance, remains circumstantial evidence. Nature, possessing a colossal volcanic arsenal, can theoretically mimic even the sharpest spikes of greenhouse gases. To unmistakably identify intelligence in the geological record, we need to find what the planet cannot create independently. We need a material whose molecular structure screams about artificial origin. If we can't find such material in Paleocene layers, let's look at what exactly we're leaving as an inheritance to the future right now. The geochemist's gaze moves from graphs on screens to the dark abyss of the ocean. Here, on the bottom, the formation of future geological layers occurs. To an outside observer, this looks like eternal peace. But instruments record an unceasing snowfall. Billions of microscopic particles slowly descend from the surface. This isn't plankton or mineral dust. These are synthetic polymers, material that didn't exist in the universe until the mid-20th century, and now covers the bottom in a solid carpet. We've entered an epoch that future geologists might call the plastic period. This material has become the main marker of our presence, eclipsing even concrete and steel. Its chemical inertness, which we so value in everyday life, becomes both a curse and an ideal black box in geological scale. Nature can create polymers like cellulose or chitin, but it never synthesizes polyethylene terephthalate or polyvinyl chloride. These complex chains are the calling card of industrial civilization. The scale of this phenomenon is difficult to grasp using familiar categories. By latest calculations, humanity has already produced more than 8.3 billion tons of plastic. This figure exceeds the total weight of all living humans and animals on the planet. And most of this mass hasn't been recycled or burned. It is set free, floating, fragmenting into micro pieces and settling in sedimentary rocks, forming a layer impossible to confuse with anything natural. The geochemist in the laboratory understands that what we call garbage is, for science, techno-fossils. This term was introduced recently to describe fossil remains of technologies that become part of the lithosphere. If dinosaur bones are replaced by minerals, while preserving shape. Plastic behaves differently. Under pressure from new layers and water, it begins to compress, becoming an integral part of stone. We're already observing the birth of new rock types, so-called plastiglomerates. There is a widespread misconception that plastic decomposes over hundreds of years. For human life, this is eternity. But for geology, it is an instant. However, here lies a perception trap. The physical destruction of a bottle to dust doesn't mean the substance disappears. The chemical bonds of polymers are incredibly stable. Even crushed to microscopic crumbs, plastic retains its unique spectral fingerprint. It doesn't disappear, it transitions to a state of synthetic sediment. Let's model a situation 50 million years forward. Plate tectonics will shift continents. Ocean floors will become mountain peaks. A future researcher conducting stratigraphic analysis will discover a strange, unnaturally sharp layer in the rock. It will be only a few centimeters thick, but its chemical composition will shock. This will be a layer with anomalously high concentration of complex hydrocarbons uncharacteristic of biological life. It is precisely this synthetic horizon we're seeking in the past. If during the Paleocene, Eocene Thermal Maximum, a developed civilization existed, following the laws of thermodynamics and economics, it should have come to inventing cheap and durable materials. They couldn't build starships from wood industry, requires universal polymers. And if they created them, where did those billions of tons go? Why don't we see traces of ancient plastic in rock cores 56 million years old? The absence of synthetic polymers in Paleocene layers is the strongest argument against the existence of a technologically advanced species there. Either their civilization followed a path of using exclusively biodegradable materials, which seems technologically improbable for global industry, or were truly the first to conceive synthesizing substances capable of outliving their creators. Plastic is our unique signature that erosion cannot erase as easily as cities. However, plastic has its durability limit. When plunging into subduction zones where oceanic crust melts in Earth's mantle, even the most resistant polymers burn, returning to elementary carbon. The tectonic conveyor works mercilessly, destroying crust and renewing the surface. If an ancient civilization existed hundreds of millions of years ago, its plastic layer could have long since been remelted into magma. But for events 50 million years old, this argument works only partially. We must also consider the transformation factor. Under high temperatures and pressures in Earth's crustal depths, a plastic layer might undergo metamorphosis, turning into a thin layer of oil or graphite with unusual isotopic composition. But even in this case, modern mass spectrometry instruments should have noticed anomalies. We see organics, we see volcanism, but we don't see traces of mass synthetic production in ancient epochs. This leads us to a frightening conclusion. Either we're looking for the wrong markers, trying to find a mirror reflection of our own history, or the great filter works flawlessly. Perhaps civilizations die long before they manage to cover the planet with a polymer layer. Or their technologies were so perfect, they left no waste. But physics laws state the opposite. Any work produces entropy. Any order generates garbage. Thus, plastic becomes a dual symbol. On one hand, it is a monument to our ecological irresponsibility, choking oceans. On the other, it is our only chance to leave a message in eternity. If humanity disappears tomorrow, it is precisely this thin synthetic layer that will tell the universe that here was intelligence capable of changing matter's structure. This is our #1 techno-fossil, but it is not the only one, and possibly not the most durable. Plastic can be crushed, melted, or eventually eaten by evolved bacteria that learn to digest polymers. Geological time knows how to find keys to any chemical locks. If we want to find something that will survive even continental movement and changing geological eras, we need to descend to the level of atomic nuclei. We need elements not subject to chemical decomposition, because their stability is determined by nuclear physics laws. In our arsenal, we have something scarier than plastic and more durable than stone. We learn to split the atom, and this process generates isotopes that don't occur in the solar system's natural environment. If the ancients possessed this power, their trace should glow in spectrometers, even hundreds of millions of years later. It is time to check the most reliable, most dangerous, and most indestructible archive, the radioactive one. Chapter 7. The Nuclear Signature. The silence of the test site, where we now stand, is broken only by the dry, rhythmic clicking of a Geiger counter. To a layperson, this sound signals alarm fey warning of invisible death. But for a geochemist, it is the sound of hope. Plastic, which we discussed earlier, can be ground to dust by erosion or recycled by future bacteria. Stone can crumble to sand, but an atomic nucleus is the most reliable keeper of information in the universe. If we want to find a civilization that disappeared millions of years ago, we need to stop looking for garbage and start looking for radiation. We're entering the territory of nuclear physics, where time is measured not in centuries, but in half-lives. These are absolute clocks that cannot be deceived or turned back. Unlike chemical reactions affected by temperature and pressure, the decay rate of radioactive elements is constant. Here our main witness enters the game. Plutonium-244. This is a heavy, long-lived isotope that virtually doesn't occur in Earth's natural conditions. Nature hasn't created it in significant quantities for more than 4 billion years. To understand the scale, look at the nuclide table through a specialist's eyes. Plutonium-239, which we use in nuclear weapons today, has a half-life of only 24,000 years. In geological scale, this is an instant. It will disappear without trace before continental outlines change. If the ancients waged nuclear war 50 million years ago, weapons-grade plutonium would have long since turned into stable uranium and lead, mixing with the planet's background noise. However, plutonium-244 is a completely different story. Its half-life is 80 million years. This means that if a hypothetical Paleocene-era civilization launched nuclear reactors or detonated powerful thermonuclear devices, a significant portion of this isotope should still be in Earth's crust. We're looking for not just elevated background radiation, but a specific artificial fingerprint that is impossible to confuse with anything else. This is a marker that screams about technological intervention. Second on our search list is curium-247, with a half-life of 15.6 million years. The presence of these elements in a geological layer would be irrefutable proof of high-technology existence. The geochemist analyzing rock cores searches for these anomalies, with the same obsession that a gold prospector watches for gleam in muddy water. But instead of gold, we're looking for violations of natural isotope proportions that no volcano or supernova can explain. Skeptics might object, can't nature create a nuclear reactor on its own? The answer is surprising. It can. In Gabon, at the Oklo deposit about 2 billion years ago, a natural nuclear reactor functioned. Conditions aligned so that uranium-235 concentration and groundwater presence triggered a chain reaction. But for an experienced isotope specialist, the difference between Oklo and Chernobyl is obvious. The spectrum of isotopes from a natural reactor has a completely different structure than remains of enriched fuel from an industrial civilization. We conducted thorough analysis of layers corresponding to the Paleocene, Eocene Thermal Maximum. We searched for traces of plutonium, -244, and curium, -247. The result, obtained by latest generation mass spectrometers, is disconcerting in its purity. We found nothing, no spikes of transuranium elements, no signs of nuclear fission on industrial scales. The 56-million-year-old layer is chemically clean of nuclear heritage. Does this mean the end of our investigation? Not quite. The absence of plutonium tells us only one thing. If a civilization existed, it didn't use nuclear energy the way we do. Perhaps they followed a different development path, or they were wise enough to avoid dirty fission technologies, immediately transitioning to clean energy, solar, wind, or even controlled fusion, which produces virtually no long-lived radioactive waste. But even green energy leaves scars on the planet's body. Solar panel, battery, and electronics production requires colossal volumes of rare earth metals. Lanthanum, neodymium, gadolinium. In nature, these elements are distributed evenly and scattered. Industry concentrates them, creating unnatural accumulations. If the ancients mass-produced electronics, we'd see sharp peaks of these metals concentrations in sedimentary rocks. This is called a technogenic geochemical anomaly. Returning to the graphs, there really are strange spikes in certain metal content in Paleocene layers, zinc, vanadium, and as we mentioned in Chapter 4, mercury. But their ratio more resembles consequences of massive volcanic activity than the structure of a high-tech dump. Geochemistry is relentless. It doesn't see complex electronics. It sees the chaos of natural catastrophes, but not the order of industrial production. There is another search method, more subtle than analyzing substance composition, looking for scars in crystalline lattices. When a heavy nucleus decays, fission fragments fly apart at enormous speeds, burning microscopic tunnels in surrounding minerals. Called fission tracks. Zircon crystals can preserve these tracks for billions of years. Even if the substance itself is washed away by water, the crystal's damaged structure remains as evidence at the crime scene. Geochemists study thousands of such crystals under electron microscopes. If radioactive dust from nuclear war had been released into ancient Earth's atmosphere, we'd find a layer of zircons with anomalously high fission track density on the surface. So far, our microscopes show only background values characteristic of cosmic rays and natural uranium decay. Earth maintains a silence that becomes increasingly deafening. We find ourselves in a paradoxical situation. We've examined the main markers of our own civilization: plastic, concrete, nuclear isotopes, rare earth metals, and none of them gives a clear match with data from the deep past. The great filter, it seems, worked cleanly. Either no one was here before us, or they were so different that our search methods don't apply to them. We're trying to see our reflection in a mirror where perhaps a completely different life form is reflected. But there is also a third frightening possibility. We're looking for traces where it is convenient for us to look on continents, inaccessible geological outcrops. We're studying pages of the stone book that accidentally survived in the library after a fire. But what if the most important chapters were intentionally torn out and destroyed by the planet itself? What if evidence existed but was melted in the gigantic furnace of Earth's depths? Earth's crust isn't a static museum, but a conveyor belt. Huge plates constantly move, collide, and dive under each other, disappearing into the molten mantle. This process, called subduction, works like a giant shredder, destroying geological documents. Most of the ocean floor, where ancient cities or factories could have stood, simply doesn't exist older than 180 million years. It was remelted. Imagine a civilization that lived primarily on coasts or islands. All traces of their activity, their metropolises, their dumps, their nuclear burial grounds, could have been dragged into subduction zones and turned into magma. In this case, even plutonium-244 wouldn't help. It would dissolve in Earth's mantle, becoming part of the general background. We might be standing on a planet that perfectly covered its tracks, using plate tectonics as the ideal concealment weapon. We've studied less than 1/10,000th of a percent of the crust. Our conclusions are based on what survived, not on what actually was. This is survivor bias on a geological scale. To break through this circle of uncertainty, we need to change strategy. If Earth so actively destroys evidence, we must go where geological time has stopped, where there is no wind, no rain, no tectonic plates. We must raise our eyes to the sky. Chapter 8. The Cosmic Archive. The call to look to the sky sounds tempting, but an astrobiology theorist staring at flickering server screens knows we're not finished with Earth yet. Before declaring our planet clean of ancient civilizations, we need to understand the mathematics of the search itself. We know what to look for: isotopic anomalies and synthetics. But did we choose the right place to dig? A computer model loaded into a supercomputer rebuilds the planet's map, exposing a fundamental error in our logic. We humans suffer from a cognitive distortion known as survivorship bias. We look for traces of the past where it is convenient for us to dig on land, in quarries, on exposed mountain slopes. But geological survey data is relentless. Humanity has thoroughly investigated less than 1/10,000th of a percent of the crust. Drawing conclusions about the planet's history based on this negligible sample is like judging the contents of a huge library by picking up a single-page fragment from the floor. The simulation on screen speeds up time, and we see how this concealment mechanism works. The main paradox lies in settlement patterns. Any developed biological civilization, like ours, needs water and transportation routes. We build our megapolises, New York, Tokyo, Shanghai, on coasts and river mouths. These are zones of maximum biological productivity and economic advantage. But from geology's perspective, these are the most unreliable places on the planet. On the monitor, we see coastal zones marked in red disappearing first. Global ocean levels in geological history have never been stable. During global warming periods, water rose hundreds of meters, flooding the lowlands where hypothetical ancient cities should have been located. Ocean turns ruins into silt, and then tectonics takes over. What was land becomes ocean shelf. And the shelf isn't a museum, it is a conveyor belt leading to hell. Here, the merciless law of seafloor renewal comes into play. Oceanic crust is born at mid-ocean ridges and moves toward continents to dive under them in subduction zones. This process completely renews the world ocean floor every 180 million years. For geology, this is an instant. If a civilization existed 200 million years ago and lived on coasts, their cities weren't just destroyed, they were physically sent into Earth's molten mantle. The astrobiologist inputs continental plate parameters into the model. Yes, there are stable zones inside continents, fake cratons, or crystalline shields. For example, the Canadian Shield or Negev Desert, where the surface hasn't changed for 1.8 million years. It would seem search there. But here we encounter the desert paradox. Ancient civilizations, like us, unlikely built their industrial centers in the middle of lifeless granite or in arid plateau centers. We search not where they lived, but where land survived. This is the classic mistake of looking for keys under a lamppost, only because it is bright there. The probability that a developed species would decide to build their analog of Manhattan in the center of geologically stable but resource, poor Siberia or Australian desert, approaches zero. Consequently, we have a situation where habitats are destroyed while preservation sites were initially empty. Modeling shows another level of complexity: sedimentary cover. Even if part of an ancient landscape survived on a continent, it might be buried under kilometers of later sediments. To find a layer corresponding to the dinosaur era or earlier periods, we often have to drill several kilometers deep. Or cities, if covered by sedimentary rocks, would turn into a layer just a couple of centimeters thick. Finding such a needle without exact coordinates is impossible. The scientist's gaze slides across probability graphs. Drake's equation is usually applied to space, but it works in time too. If we assume the industrial phase lasts only a few thousand years, while geological epochs span tens of millions, the chance of hitting another civilization's existence window with random drilling is negligibly small. We could walk over predecessors' bones, drill through compressed cities, and not even notice, mistaking them for strange geological inclusions. The Cannibal Earth theory explains the absence of direct evidence better than the hypothesis of human uniqueness. The planet is an active thermodynamic machine whose main goal is mixing and remelting matter. Entropy here works not through slow decomposition, but through active tectonic destruction. For the laboratory observer, this means a dead end. We're trying to read a book whose pages have been torn out and thrown into a fireplace. However, this pessimistic modeling conclusion opens an unexpected door. If Earth so aggressively destroys its history, then to search for our planetary system's black box, we need a place devoid of this aggression. We need a world without water, without wind, without volcanoes, and most importantly, without plate tectonics, a world frozen in eternal silence, preserving every scar received over billions of years. On the supercomputer screen, Earth's model recedes, giving way to its satellite. The Moon is the ideal geological archive. Erosion there proceeds at a rate of 1 millimeter per million years. If someone visited Earth, or if an Earth civilization ever left its cradle, traces of this should have remained on the Moon practically forever. There, in gray regolith dust, a boot print or landing support could wait for discovery through eras and epochs. The astrobiologist's thought crystallizes into a new search strategy. Instead of sifting through tons of Earth rock hoping for a miracle, we should pay attention to our celestial neighbor. The Moon doesn't know how to keep secrets the way Earth does. It is a witness that never blinks. Everything that ever happened in Earth's vicinity is recorded on its surface. It is time to read these records. Chapter 9. Lunar Archaeology. Logic is relentless. Any civilization reaching our level of development inevitably goes to space. Satellites, probes, landing modules, these are technosignatures not subject to terrestrial corrosion. If an industry existed on Earth, it should have left a mirror trace in orbit or on the Moon. The absence of such traces, there would be much weightier proof of our solitude than empty excavations on Earth. For a planetologist observing the satellite's surface through mission control monitors, this gray landscape doesn't look like a desert, but like an untouched library. Here, there is no wind to sweep away tracks, no water to erode stone, no moving plates to drag evidence into magma. Vacuum preserves matter in ideal stasis. The only thing happening here is silence lasting billions of years. The gaze slides across data transmitted by the Lunar Reconnaissance Orbiter. This apparatus's cameras shoot the surface with resolution down to 50 centimeters per pixel. This allows us to see not just mountains, but individual boulders. The planetologist isn't looking for geology. He is looking for geometry. Nature favors fractals and chaos, right angles, perfect circles, or symmetrical constructions are an engineer's handwriting, not coincidence. The main argument favoring lunar searches is the incredibly low erosion rate. According to lunar rock analysis data, the surface wears away at approximately 1 millimeter per million years. Consider this number. A layer of dust, the thickness of a coin, accumulates here longer than the entire Homo sapiens species has existed. This means any object left on the moon in the age of dinosaurs would look today almost the same as on the day of its creation. The only enemy of preservation here is micrometeorite bombardment and space weathering. Solar wind slowly darkens soil, and tiny grains flying at cosmic speeds work like a delicate sandblasting machine. But this process only softens sharp edges. It doesn't destroy structure. A large metal object, such as a landing module or habitat block, could survive geological epochs here. We already have proof of this phenomenal conservation. Neil Armstrong and Buzz Aldrin's boot tracks left in the Sea of Tranquility in 1969 remain untouched. The flag's fabric has probably faded under harsh ultraviolet, turning to white plastic, but its very form and the ribbed sole prints in regolith will be preserved for millions of years. This is our standard. If we see traces half a century old, we'll see traces 50 million years old. The search logic is merciless. An industrial civilization cannot exist in isolation on a planet's surface. Technology development inevitably requires satellites for communication, navigation, and weather monitoring. And any satellite eventually falls or requires orbital servicing. If the ancients possessed at least mid-20th century technology levels, they were obligated to leave their Apollos, their lunar rovers, or at least rocket stages that crashed into the surface. The planetologist focuses attention on a strange object inside Tycho crater. In the grainy image, a structure is visible casting an unnaturally long and straight shadow. This is the moment for which all anomaly detection algorithms work. In a world of chaotic debris ejected by asteroid impacts, a professional's eye instantly catches order. Could this be the tip of an obelisk or the edge of an ancient module half buried by regolith? Here we encounter the pareidolia phenomenon, the brain's property to see familiar images in random textures. In the 70s, low-resolution images made many believe in a face on Mars, which turned out to be just a play of light and shadow on an ordinary hill. But today we have tools to check hunches. Spectral analysis allows determining material composition from orbit. Titanium, aluminum, purified glass. These materials don't grow on the moon. However, even with perfect maps, we haven't fully explored the moon. Its surface area is comparable to Africa's. Finding a car-sized object there is a non-trivial task. We're looking for a needle in a haystack, the size of a continent. But unlike Earth, this haystack doesn't rot or change shape. If the needle is there, it will glisten in sunlight, reflecting light differently than surrounding basalt. There is another aspect: burial depth. The regolith gardening process, where constant meteorite impacts mix the upper soil layer, could bury small artifacts several meters deep over hundreds of millions of years. What lies on the surface we see, but what was left in the age of dinosaurs might be hidden under a thin gray shroud. For their detection, we'd need not just cameras, but ground, penetrating radars capable of looking under the satellite's skin. Nevertheless, the absence of obvious lunar bases in LRO images is already a powerful scientific result. This is so-called data silence. If an ancient civilization was expansive, colonizing space, the moon would be littered with their debris just as Everest is littered with oxygen tanks. We humans, in just half a century, left more than 200 tons of equipment there. If they were more powerful than us, their dumps should be visible through amateur telescopes. This leads us to an important conclusion about hypothetical predecessors' nature. If they existed, they probably weren't a space-faring race. Perhaps they got stuck in Earth's gravity, unable or unwilling to overcome escape velocity. Or their space era was so brief, they didn't manage to litter the neighboring celestial body. The moon is clean. Its pristine emptiness frightens more than any ruins. But the lunar surface isn't the only place where time stops. In cosmic space, there are points where Earth's and the Sunday's gravity balance each other, creating unique stability zones. These are the so-called Lagrange points. If the moon is a museum, then Lagrange points are gravitational traps, fade dusty corners of the solar system where forgotten things can hang forever, requiring not a drop of fuel to maintain position. Astronomers call these zones Trojan points. Mathematical modeling shows that asteroids and dust can accumulate there and orbit in stable trajectories for millions of years. This is the perfect place to park a space station, beacon, or ship graveyard. If someone wanted to leave a message in a bottle guaranteed to be found by future generations, they would throw it precisely into these gravitational backwaters. Paradoxically, finding a tiny probe in the emptiness of a Lagrange point might be easier than finding a module against the lunar landscape's variegated background. In open space, any object emitting heat or reflecting light unnaturally becomes a beacon. We've already begun scanning these areas, searching for asteroids threatening Earth. But our telescopes could also notice polished metal gleam among dark stones. The moon gave us a negative answer, but this answer is important. It cuts off an entire branch of probabilities. We didn't find cities, factories, or giant quarries there. So if there was a civilization before us, it was either chained to Earth or developed along a path we find hard to imagine without heavy rockets and orbital expansion. The Lunar Archive is empty, but there are other caches in the solar system. We rise higher up the cosmic search ladder, from the satellite's solid surface to invisible gravitational pockets, and then to other planets. Mars, with its dried riverbeds, might preserve what the moon never had, traces of life. But before we head to the red planet, we need to check those very gravitational attics of Earth, where ancient epochs' debris might have accumulated awaiting our visit. Chapter 10. The Gravitational Attics. We're accustomed to seeing the moon as the main keeper of secrets, but the solar system's gravitational map is much more complex. If the satellite is an open square bombarded by meteorites, then space has hidden basements where even a random asteroid doesn't peek. An astrobiologist modeling ancient civilizations' behavior knows If you want to hide something for 1 billion years, you don't put it on a planet's surface, Faye. You send it to a point where physics stops time. We're talking about Lagrange points, Faye unique equilibrium zones. On supercomputer monitors, these zones look like perfect gravitational wells. In a system of two massive bodies, like Earth and the Sun, 5 points exist where centrifugal force balances gravity. 3 of them are unstable. Any object getting there will eventually be ejected like a ball from a hilltop. But 2 points, Faye L4 and L5 Faye, work differently. They're located at the vertices of equilateral triangles with the Earth, Sunday base. These are cosmic traps. Everything that falls into their gravitational embrace remains there forever. For the theorist, this changes the search paradigm. We don't need to scan the entire sky. Physics dictates the cemetery's coordinates. If millions of years ago a communication satellite, navigation beacon, or automatic probe was launched into orbit, after exhausting fuel, it wouldn't fall to Earth or fly to the stars. Gravitational currents would slowly but surely carry it precisely to these points. L4 and L5 are the Sargasso seas of space, where debris from all eras drifts, and if there is anything there besides dust, it is still there. In 1961, Polish astronomer Kazimierz Kordylewski noticed a faint glow at these points. Later, the existence of dust clouds receiving his name was confirmed. This is cosmic dust accumulation captured by Earth's gravity, but what is important for us is different. The very fact of Kordylewski clouds' existence proves the trap's stability. Nature stores its microscopic archives there for millions of years. The question is whether a titanium alloy or ceramic hull got lost among trillions of dust particles. We're looking for so-called Earth Trojan asteroids. Jupiter has thousands of them, but our planet's first such satellite, Faye asteroid, 2010 TK7 Faye, was discovered only in 2010. This is a rock about 300 meters in diameter that obediently hangs at point L4. The astrobiologist sees this not as just a stone, but as ideal cover. If I wanted to create an autonomous station for observing life development on Earth, I'd disguise it as such an asteroid or hide it in its shadow. This is the perfect position, stable orbit, constant view of the planet, and eternal protection from tidal forces. The hypothesis about observer probes or Bracewell probes suggests that a developed civilization would prefer to leave autonomous artificial intelligence rather than fly itself. Such an apparatus could be in sleep mode for eons, activating only upon detecting radio signals. Lagrange points are the only place in Earth's vicinity where such an apparatus could survive without orbit correction. We're only beginning to understand that we've been looking for alien intelligence too far away while its black box might be hanging in our orbit. But detecting an artificial object at Lagrange points is harder than finding a needle in a haystack 150 million kilometers away. Optical telescopes see only reflected light. If a hypothetical ancient apparatus is painted black or covered with a cosmic dust layer, it becomes invisible to optics. It merges with emptiness. The astrobiologist understands. We need to search not visually but thermally. Any working electronics, even in deep sleep mode, releases heat impossible to hide from thermodynamics laws. The James Webb Space Telescope and future infrared survey missions could spot a thermal anomaly against cold space background. We're looking for a spectral signature that doesn't exist in nature. Asteroids consist of silicates, iron, and nickel. If spectral analysis indicates purified aluminum, titanium, rare earth metals, or complex polymers at point L5, this would be direct proof of technological origin. Nature doesn't create alloys and plastic in vacuum. Recent research by astronomers searching for so-called co-orbital objects has yielded negative results. We found several small asteroids, but none emit radio signals or have anomalous thermal signatures. The silence at Lagrange points is deafening. This is a serious blow to the hypothesis of ancient space expansion. If they had gone to space, a debris belt around points L4 and L5 would be inevitable. The absence of debris speaks more eloquently than any theories. However, there is a nuance that troubles the astrobiologist. We've scanned these areas expecting to see large objects, space stations, ships, huge antennas. But technology tends toward miniaturization. What if their legacy is a swarm of nanosatellites, the size of dust grains? Smart dust distributed in orbit would be indistinguishable from natural Kordylewski clouds using our current instruments. We might be looking directly at their Library of Congress, but seeing only a cloud of cosmic dirt. Additionally, Lagrange points aren't absolutely safe. Though gravitationally stable, they're subject to solar wind and micrometeorites. Over 50 million years, any unprotected object would turn into Swiss cheese. Space erosion is slow but merciless. If ancient engineers didn't provide self-repairing materials or powerful force fields, only clouds of molecular debris would remain from their satellites. Fey debris we now take for natural dust. We must also consider intentional disposal, an ecologically responsible civilization. Recognizing Kessler syndrome risks. Fey uncontrolled orbital debris collisions. Fey might intentionally deorbit their apparatus at end of service life. They could direct them toward the Sunday or return them to Earth's atmosphere for burnup. The cleanliness at Lagrange points might testify not to technology absence, but to the highest culture of space stewardship that we haven't yet achieved. Nevertheless, negative results at Lagrange points narrow the search circle. We didn't find cities on Earth, bases on the Moon, or orbital stations in gravitational traps. This leads us to two conclusions. Either a civilization existed, but was strictly terrestrial, lacking ambitions or ability to leave the atmosphere. Or we're searching on the wrong planet. Perhaps Earth wasn't home, but just a temporary colony or visit target. The astrobiologist's gaze moves further to the fourth planet from the Sunday, Mars. Today, it is a dead desert, but 4 billion years ago, it was Earth's twin with oceans and dense atmosphere. If Earth is an active washing machine destroying evidence through tectonics and water, then Mars is a freezer. Plate tectonics stopped there billions of years ago. Erosion is minimal. If someone walked on red sand in deep antiquity, their tracks might be fresh, as if left yesterday. The hypothesis that life or even intelligence could have originated on Mars and then migrated to Earth sounds like fantasy. But from a ballistics perspective, it is simpler than it seems. Matter exchange between planets goes on constantly through meteorites. But could they have left technosignatures there? Mars rovers already find strange chemical anomalies, and some isotopic atmospheric data raises disturbing questions among physicists. We're heading where planetary catastrophe already occurred. Mars offers us a unique mirror. This is a planet where geological time froze. If we want to see what civilization ruins look like after hundreds of millions of years, we don't need computer modeling. We need to look at images of Valles, Maranaris, and Gale Crater. Perhaps what we take for bizarre rocks is actually the melted framework of ancient metropolises, destroyed not by time, but by something much more terrible. Chapter 11. The Red Planet's Silence. Mars isn't just a neighbor, Faye. It is our geological opposite. If Earth is a raging ocean of tectonic activity that grinds its own history every 200 million years, then Mars is a giant open-air museum. Here, the planetary conveyor belt stopped billions of years ago. For an operator receiving telemetry data with a 20-minute delay, Mars looks like a graveyard. But this is a graveyard with perfect preservation. There are no rains to wash away foundations, no crustal shifts to drag cities into magma. Valsmarineris Fae, this monstrous scar on the planet's face, Fae remains unchanged longer than all multicellular life has existed on Earth. You must understand the scale of tragedy frozen in red sand. 4 billion years ago, when Earth was still a molten ball unsuitable for life, Mars was already a blue planet. It had dense atmosphere, magnetic field, and deep oceans. This was paradise in the solar system, long before the first microbe appeared in Earth's puddles. If the first technological civilization of our system was to arise anywhere, it should have been here. The planetologist looks at images transmitted by orbital apparatus and sees not just craters, but channels of dried rivers, deltas where water once splashed. If Martians existed and built their cities from concrete and steel 3 billion years ago, their ruins wouldn't disappear without trace as on Earth. They'd be covered by sand, eroded by wind, but their geometry would still be readable from orbit. However, the HiRes high-resolution camera, capable of distinguishing objects the size of a dining table, shows us only chaos of stones. We don't see highways, foundations, or quarries, but the absence of visual traces returns us to this investigation's main methodology: chemistry. Eyes can deceive, mistaking shadow play for a sphinx's face, but a mass spectrometer doesn't know how to lie. The Perseverance rover is currently drilling the surface in Jezero crater. Its drill bites into sedimentary rocks formed in water's presence. We're looking for biosignatures, Fae traces of primitive life, Fae, but the rover's instruments, like the Sherlock spectrometer, don't distinguish between biology and technology. They don't care whether they find a fossilized bacterium or a complex polymer molecule that couldn't arise naturally. Here, in atmospheric gas analysis data, we stumble upon one of modern planetology's most disturbing mysteries. This anomaly makes nuclear physicists nervously exchange glances. We're talking about xenon-129 isotope concentration. On Earth, this noble gas in such proportions is extremely rare and typically associated with a specific process, nuclear decay. Xenon-129 is one of the markers arising after nuclear device detonation. Its concentration in Mars' atmosphere is significantly higher than in solar wind or on other celestial bodies. Dr. John Brandenburg, a plasma physicist, proposed a bold, borderline, insane hypothesis. Martian atmosphere wasn't just lost Fae, it was destroyed by a series of powerful nuclear explosions in the distant past. This theory sounds like a cheap action movie script, and most of the scientific community treats it skeptically. Natural models exist, explaining excess xenon-129 through iodine-129 decay in the planet's early crust. But the very fact that we're forced to seriously discuss the difference between natural catastrophe and ancient nuclear war shows how thin the line is in interpreting data from another planet. If we discard exotic war theories, one fact remains: Mars is dead. Its magnetic dynamo stopped. Solar wind stripped the atmosphere, and the surface was sterilized by harsh ultraviolet and perchlorates, Fae salts, making Martian soil toxic to Earth life. Any organics remaining on the surface would be oxidized and destroyed over millions of years. We're searching for traces in a world that went through a global disinfection procedure. But even in this dead world, there are oddities. In the area known as the City of the Incas, probes detected geometric structures resembling wall ruins. Geologists explain this as magma intrusion into sedimentary rock fractures and subsequent erosion. This is undoubtedly the most reasonable explanation. Nature is a talented sculptor, and the human brain tends to see order where there is only entropy. Nevertheless, we must admit, we've studied Mars worse than Earth's ocean floors. Our rovers have traveled a total of several dozen kilometers across a planet whose land area equals all Earth's land. Drawing final conclusions about civilization absence based on 2 or 3 machines' routes is like landing in the Sahara, driving 5 kilometers, and declaring that cities never existed on Earth. Perhaps we're looking in the wrong place. If Martian civilization existed, it might have gone underground, escaping atmospheric loss. Huge lava tubes discovered on Olympus Mons slopes could house entire metropolises protected from radiation by rock thickness. But our satellites can't look inside, and rovers can't descend into these abysses. In the dry residue, we have a mirror planet. Mars shows us Earth with a stopped heart. We found no obvious technosignatures. There no plastic mountains, no processed metals, no reactor backgrounds. The xenon isotopic anomaly remains a tantalizing hint, but insufficient for a verdict. If someone lived there billions of years ago, they left as quietly as they came, leaving the planet to wind and red dust. We've checked Earth, the Moon, Lagrange points, and Mars' surface. Physical evidence is absent or reliably hidden. This brings us to our investigation's most frightening stage. If space is silent, perhaps the answer lies in time. Maybe the problem isn't where to look, but how often intelligence can arise in the universe at all. We must turn to probability mathematics. Chapter 12. The Mathematics of Extinction. Physical search has reached a dead end. We found no golden plates on the Moon, no abandoned ships on Mars, no orbital stations in gravitational traps. But in science, a negative result is still a result. If space is silent, the astrobiologist must change coordinate systems. In the echoing cold of a server room, where a supercomputer models planetary system evolution, the question, where are they, transforms into a more precise mathematical formulation. We're used to applying Drake's equation to space, trying to calculate the number of intelligent worlds in the Milky Way right now. But this is three-dimensional beings' thinking error. To see the full picture, Drake's equation must be unfolded in time. We must ask not how many are there in the sky, but how many were here under our feet, over Earth's 4.5 billion years of existence. For the theoretical model I observe on monitors, Earth isn't humanity's unique home, but a multi-apartment complex where tenants constantly change. The main parameter here is temporal resource. Complex multicellular life has existed on the planet for about 400 million years. This is a colossal time span in which human history fits like an instantaneous flash, barely distinguishable on the graph. We input a biological constant into the simulation, mammalian species average lifespan. The paleontological record is merciless. On average, a species lives about 1 million years. After this, it either goes extinct or evolves into something else. Homo sapiens, by the most optimistic estimates, has existed 300,000 years. We haven't passed even a third of nature's standard allotted path. Now, Let's overlay the industrial phase duration on this graph. Our technical civilization, capable of changing planetary chemistry and emitting radio waves, has existed only 200 years. In geological scale, this is 1/20 millionth of the time life has existed on land. This isn't even a second in a day, it is a fraction of a moment. This brevity creates a frightening statistical paradox. Mathematical modeling allows for up to 5 industrial civilizations in Earth's past that could have developed, flourished, and disappeared without ever intersecting in time. If we divide biosphere history into 100 million-year segments, each has enough time for intelligence evolution from scratch, empire creation, and complete oblivion. Suppose 70 million years ago, in the Cretaceous period, some theropod species developed 18th century level intelligence. They built wooden cities, used water mills, and forged iron. Existing for 5,000 years, longer than all our written history, they perished from virus or climate shift. What would remain of them today, after 70 million years? The system's answer is unambiguous: nothing. Iron would oxidize to dust in a couple millennia. Wood would rot, stone would crumble to sand. Without plastic production or nuclear reactions, we saw it in past chapters, such a civilization becomes invisible. The geological record has too low resolution to notice events lasting 5,000 years. This is time pixelation problem. We see the dinosaur era as a continuous age of giants. But actually, we find one skeleton per tens of thousands of years of their history. The probability of finding remains of a specific intelligent species representative that lived compactly and briefly statistically approaches zero. We look at Earth's history through murky glass, distinguishing only the largest catastrophes. This is where the Kardashev scale concept appears on screen. We humans haven't even reached the first type. We don't use all energy falling on the planet from our star. We're a type 0.73 civilization. This means our energy consumption, though enormous for us, is still negligibly small compared to natural processes, hurricanes, volcanism, and tectonics. If hypothetical predecessors were wiser than us and didn't strive for infinite consumption growth, if they remained in harmony with the biosphere without burning oil or splitting atoms, they signed their own oblivion sentence. Green civilization using biodegradable materials and renewable energy is a future archaeologist's worst nightmare. It leaves no scars on the planet's body. Simulation shows another disturbing aspect: the bottleneck effect. Intelligence emergence needs specific conditions: high oxygen levels for large brain operation, land presence, climate stability. These opportunity windows opened infrequently on Earth. Carboniferous, Jurassic, Eocene periods. Each time, nature rolled dice. But why? If probability isn't zero, don't we see even indirect signs of their expansion? Why didn't any of them go to space, leave orbital satellites, or colonize the moon? Modeling leads us to a harsh thermodynamic limitation. Perhaps intelligence isn't evolution's gift, but a dangerous mutation leading to rapid self-destruction. Look at the entropy growth graph. Any complex structure, whether city or organism, maintains its order by creating chaos in the environment. The more complex and powerful a civilization, the faster it depletes its ecological niche resources. This is a universal physics law that can't be cheated by technology or ideology. The time equation gives us an answer we don't want to accept. Civilizations might be frequent phenomena, but they're always short-term. They flare like matches in darkness, fade bright, hot, and very briefly. The gap between these flashes is tens of millions of years of silence and biosphere recovery. We're alone, not because we're first, but because we're the only ones now. The supercomputer completes calculating another scenario. The probability that Earth produced us as the only intelligent beings in 4.5 billion years is less than 10%. But the probability that we'll find physical evidence of others is even lower. We're trapped in our temporal layer, cut off from the past by geological decay walls. This realization changes our search's very meaning. We looked for predecessors to learn our fate. We hoped to find those who survived technological adolescence and reached maturity stage. But the silence of ancient rocks and space emptiness hints that the maturity stage might be an unattainable dream. Perhaps there is a barrier no one can overcome. In astrophysics, this barrier is called the Great Filter. This hypothetical event or natural law prevents life from developing to interstellar civilization level. And if we found no one who passed this filter before us, it is still ahead, and we're rapidly approaching it. The question is only what exactly this filter represents. If this mysterious great filter really exists, then we should look for it not in space depths, but in physics laws themselves governing our world. Looking at the global catastrophe model, the paleoclimatologist sees not just destruction, but inevitable balance restoration. For the planet, advanced civilization death isn't tragedy, but a cooling mechanism. It is like immune system operation. When one species' activity threatens biosphere integrity, processes activate that return the system to its initial state. The fundamental problem of any highly developed structure is described by the second law of thermodynamics. This law is merciless. It is impossible to create order at one point without increasing chaos around it. We build cities, structure information, and create complex machines. But payment for this local order is always heat emission and environmental chemical pollution. This isn't design error or malicious intent. It is a physical constant. The more complex a civilization, the more entropy it must dump into the external world to avoid crumbling. This contains the paradox we call the progress trap. Technology development allows us to extract resources faster and more efficiently, leading to explosive population and consumption growth. But the planet is a closed system with finite energy reserves and regeneration capacity. When civilization reaches a certain power level, it begins consuming resources faster than geology can replenish them. We burn in a century what accumulated for hundreds of millions of years. This equation has no positive solution in the long run. Mathematical modeling shows a frightening correlation. The higher the technological level, the shorter the species' lifespan. The Stone Age lasted hundreds of thousands of years in relative equilibrium with nature. The agricultural era took millennia. The industrial phase burns the planet in a couple centuries. Any technological civilization's development graph doesn't look like a smooth ascending line, but like a vertical needle. Sharp rise, peak consumption, and inevitable collapse under its own success weight. It is precisely thermodynamics that explains what astronomers call universe silence. If this scenario is universal, galactic civilizations simply don't have time to meet. They flare and fade in their planetary systems, separated not only by light years but by insurmountable time chasms. The period when an intelligent species possesses radio communication and powerful industry might be only a few hundred years, after which it either dies or is forced to slide into technological medievalism. There is another filter, passing option. But it makes civilization invisible to our instruments. Transition to homeostasis, complete equilibrium with environment. Theoretically, superdeveloped intelligence should understand infinite growth's dead end and consciously stop its expansion. But such civilization stops emitting radio waves, stops releasing carbon, stops changing climate. It becomes quiet and indistinguishable from natural background. We don't see them not because they don't exist, but because only those who know how to hide survive. However, for a young and aggressive species like humanity, this path seems impossible. Our evolution sharpened us for expansion. We're descendants of those who always wanted more food, more territory, more resources. Biological imperatives formed in Pleistocene savanna conflict with nuclear-era capabilities. We possess God's technologies, but manage them with primate instincts. This gap between tool power and operator wisdom might be that very great filter. Geological record confirms no dominant species held the throne forever. Dinosaurs ruled 160 million years, but disappeared. Trilobites prospered 270 million years. We, with our tiny 200,000-year term, are in statistical error range. Nature doesn't tolerate monopoly. As soon as one species begins consuming too much, climate changes, food chains collapse, and the system harshly resets the leader, freeing the niche for evolution's new experiments. Looking at the extinction graph, we can notice cyclicality resembling breathing. Every 26-30 million years, the biosphere undergoes serious cleaning. Some of these events are caused by external factors like asteroids, but many are provoked by life's internal processes. Photosynthesizing bacteria appearance 2.5 billion years ago led to an oxygen catastrophe that killed almost everything living. We're doing the same, but using carbon dioxide and plastic instead of oxygen. The collapse scenario always develops exponentially. Complex systems, like our global economy or Earth's ecosystem, possess a safety margin allowing them to ignore damage for long periods. But when elasticity limit is passed, destruction occurs like an avalanche. The paleoclimatologist on the drilling platform knows climate changes unevenly, it switches in jerks. The system accumulates tension for years to discharge in one decade's catastrophe. Imagine an ancient civilization facing the same choice as us. They could recognize the threat, but like us, found themselves hostage to their infrastructure. You can't just stop factories without dooming billions to starvation. It is a trap to solve problems created by technologies. We need even more powerful technologies that, in turn, create new problems. This circular race accelerates until centrifugal force tears systems apart. When dust settles, the great equalizer takes effect. Time, oceans absorb coastal metropolises. Acid rain dissolves concrete, and plant roots crack asphalt. In 10,000 years, global empire greatness becomes strange hills overgrown with forest. In 1,000,000 years, even these disappear. The planet erases the failed draft to prepare a clean sheet for intelligence's next attempt, if such attempt occurs at all. This ruthless cycle explains why we found no predecessors, not because they didn't exist, but because their very existence triggers their destruction mechanism. Advanced civilization isn't a planet's evolution stage, but rather an acute infection that Earth successfully treats with global warming fever. We look for city traces, but perhaps we should look for scars. Scars on the planet's geological body left by those who also tried to conquer thermodynamics. Now, understanding erasure mechanisms, our universe loneliness acquires new meaning. We're not just looking for intelligence brothers, We're looking for proof that intelligence can survive its own technological adolescence. The absence of clear signals and artifacts is a grim warning. It is a hint that the great filter barrier is almost impassable, and right now humanity is rushing toward it at full speed. However, this frightening conclusion contains paradoxical hope. If we understand the trap mechanism, we have a chance to avoid it. We're the first Earth civilization that doesn't just change climate, but knows it is doing so. Dinosaurs didn't see the asteroid. Bacteria didn't know chemistry. We know. And this knowledge imposes responsibility far beyond our own survival. Perhaps the very ability to forecast will be the factor allowing us to break this vicious cycle. But even if we find a path to sustainable existence, we can't cancel physics laws. Stars aren't eternal, the planet cools, the universe expands. Ultimately, entropy will defeat any structure, however wise. The question isn't whether we'll disappear. The question is what will remain after us when the last monitor screen goes dark and the last generator stops. Epilogue: the cosmic perspective. Leaving Earth's orbit, we watch our planet turn into a lonely blue dot lost in infinite blackness. All those colossal epochs we explored from scorching Paleocene to icy Pleistocene shields, merge here into a single fragile moment of the present. Looking at this receding sphere, we must acknowledge the harsh truth that geology revealed to us. The universe is indifferent to our ambitions. It doesn't keep archives. Planetary renewal mechanisms, tectonics, erosion, crustal remelting, work flawlessly, erasing any physical evidence of greatness. Whether stone pyramids or glass, concrete skyscrapers, we began this journey with an audacious question: who was before us? We sought predecessors, hoping to find comfort in the thought that civilization is a repeating cycle, not a random anomaly. We sifted through isotopic data from the last 500 million years, studied thermal maximum anomalies, peered into lunar craters, and Lagrange point gravitational pockets. Everywhere we met, only silence. No processed plutonium-244. No synthetic polymers in Paleocene layers. No geometrically correct ruins on Mars. This silence is the loudest answer we could receive. The absence of evidence certainly isn't strict proof of absence. However, the probability of developed industrial civilization existing in the past approaches statistical error. This leads us to a conclusion both frightening and elevating. We're most likely the first. We're the first spark of intelligence that doesn't just exist but can recognize its mortality and attempt to cheat entropy. For 4.5 billion years, Earth was a blind stage for biological evolution. Only in the last moment did an observer appear on this stage. The Silurian hypothesis we began with ultimately proved not so much a tool for searching the past as a mirror for our future. Those very markers we sought in vain in ancient rocks, sharp carbon-12 jump, plastiglomerate layer, radioactive isotopes, this is precisely the legacy we're inscribing into geological record right now. We're creating a technosphere whose mass, by 21st century estimates, already exceeds 30 trillion tons. We're those very mysterious predecessors whose traces future geologists will try to decipher in 50 million years. But what exactly will they find? If our civilization collapses tomorrow, in 100,000 years, only thin layers of strange chemistry will remain from our cities. Rust will devour steel, concrete will turn to sand, and books and digital media will disappear instantly. Humanity's only monument will be a thin, dark line in sedimentary rocks saturated with rare earth metals and microplastic. This is our autograph in Time's book. The irony is that the more advanced technology becomes, the less durable its carriers. A stone axe lives millions of years. A hard drive fades decades. However, our existence's meaning can't reduce to leaving behind a pile of garbage the planet can't digest. We encountered Fermi's paradox and the great filter concept, not to fall into despair. Understanding that thermodynamics works against complex systems gives us an advantage. Previous species went extinct because they couldn't foresee catastrophes. We possess a unique tool, predictive modeling. We know resources are finite. We know the star evolves. We know staying in the cradle means dooming ourselves to death. Our research confirmed that time isn't just duration fey. It is a physical force destroying structure. In 1 billion years, solar luminosity will grow 10%, leading to ocean evaporation and plate tectonic cessation. Earth will become sterile, like Venus. This is a hard deadline set by astrophysics. We don't have eternity in reserve. Any civilization locked on one planet is mathematically doomed. Therefore, searching for traces on other planets wasn't just curiosity, but seeking emergency exits that perhaps no one before us managed to use. In this context, our loneliness stops being frightening and becomes motivating. If the universe is silent, then we're its voice. If there was no one in the past who could break free from the gravity well and overcome the great filter, then this mission falls to us. We bear responsibility not only to ourselves, but to life itself. We're keepers of the only known flame of intelligence within billions of light years. Letting it extinguish due to internal conflicts or ecological short-sightedness would be a cosmic-scale crime. Earth's history teaches us humility, but science gives us hope. We no longer seek ghosts in planetary machinery. We understand that becoming a ghost is our fate. If we don't move to the next step on Kardashev's scale, our task is to transform that very techno-signature we're creating from a deceased civilization's epitaph into a foundation for something greater. Lunar tracks won't erode for millions of years. This is the first step toward species immortality impossible on one constantly changing planet. This film was an attempt to peer into time's abyss, and the abyss looked back at us. If you, like us, feel this sacred awe before history's scale and our moment's fragility, stay with us for future investigations. Your attention and science support is the resource allowing us to continue asking uncomfortable questions and seeking answers, however frightening they might be. We'll continue disassembling the universe atom by atom to understand our place in it. Ultimately, it doesn't matter whether we were first. What matters is whether we'll be the last. The universe is a dark forest, and so far we're its only light source. We found no traces of ancient gods because gods aren't those who were in the past. They're what we can become if we learn to value the time allotted to us. Earth will forget us. The Sunday will burn our archives, but light sent by us to the stars will fly forever.